The questions are not spoken aloud during the test, only comments on the answers. Read a question through and work out your answer. Use the datasheet on page 225 of the textbook when necessary. Then press play to check your answer and listen to the comments. You'll need to turn autoplay off to get the best effect. Keep a check of your score as you go along. There are 19 questions and 80 marks to be scored. Momentum is mass times velocity. That gives the unit for momentum to be kilograms multiplied by meters per second. So the answer can't be D because you are asked which of the options is not a unit for momentum. Both A and C are equivalent units for momentum. In option A, Newton seconds expands to kilogram meters per second squared multiplied by seconds, which simplifies to kilograms multiplied by meters per second, the unit for momentum. In option C, joules per meter seconds expands to Newton meters multiplied by seconds per meter, which simplifies to Newton seconds, which is option A, one we have already ruled out. So the answer must be B. You could have been brave and chosen B straight away because it contains meters per second squared, and this is the unit for acceleration. But sometimes it is reassuring to work things out the long way, if you have time. Rockets use Newton's third law, which states that the force of one body X on another Y is equal and opposite to the force of body Y on body X. In this case, the rocket pushes exhaust gases backwards, and the exhaust gases push the rocket forwards. So the answer is C. Both a singly ionised helium atom and an ionised hydrogen atom have lost one electron, and so both carry a charge of plus 1.6 times 10 to the minus 19 coulombs. On acceleration in an electric field, the kinetic energy gained is calculated by multiplying the charge by the accelerating potential difference. Note that this expression is independent of the mass, so the ions will each gain the same kinetic energy. So the answer is A. The expression for centripetal acceleration is shown here. This rearranges to this expression for the radius r. We now need the centripetal acceleration A. Using F equals m multiplied by A, and rearranging, we get an expression for calculating A. Substituting and calculating, you can see that the acceleration is 8.46 meters per second squared. Substituting in the expression for the radius r and calculating shows that the radius required is 19.98 meters, which is 20 meters to two significant figures. So the answer is A. You should know that dipoles have opposite electric charges at each end. This means that in a uniform electric field they twist rather than accelerate because their net charge is zero. So the answer is either C or D. The two opposing forces will finish up acting along the same line. Draw a sketch if you are in doubt. So the answer must be option D. This means that 3 statements are correct. Options C and D look okay, but what about A and B? You know about the Earth's magnetic field, and you know that there is often lightning during a thunderstorm, which is produced by huge electric fields. So the answer must be A. Of course, an electric current in a wire does create a magnetic field, But the wire remains neutral because the charge on the electrons carrying the current is balanced by the charge on the protons in the atoms of the metal wire, so there is no electric field around the wire. It seems at first as if you need to use the relationship between the force F on a particle with charge Q moving with velocity v in a uniform magnetic field of flux density B, where θ is the angle between the particle's direction of motion and the magnetic field. But just think a little, read the question again, and note that it says along the magnetic field lines. Yes, it is a bit of a catch because you don't need any of the data since sine θ is equal to 0. So the force must also be 0. Inside the Ds, the protons are shielded from electric fields. The only force they feel is the centripetal force BQV produced by the magnetic field. This magnetic field is perpendicular to their motion, and the BQV force is perpendicular to their motion, that is, to their path. So don't be tempted by the alternatives until you have tried to complete the sentence yourself. The reason they travel at constant speed, but not constant velocity, is that the magnetic force on them is perpendicular to their path, and there is no electric force on them while in the Ds. In other words, there is no force then acting on them along their path. So the answer is B. You need to be careful here because of the quantity 1.6 giga-electron volts. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So 1.6 giga-electron volts is given by this expression. Now the mass m, as given in the question, can be worked out using this expression. Substituting and calculating shows the mass to be 2.8 times 10 to the minus 27 kilograms, which makes option C the correct answer. You must have the same number of baryons on each side of a possible reaction. Both protons, P, and neutrons, N, are baryons, but all the pi particles are mesons. The only reaction which has this condition is option D, with 2 baryons on each side. This is all about the impulse momentum equation. The force F multiplied by the time it acts for, delta t, is equal to the change in the product of the mass and the velocity, delta mv. In this case, the mass of the sprinter stays the same, so the expression simplifies to the mass multiplied by the change in velocity. In part A, the area under a force time graph represents the change of the sprinter's momentum. The small area below the time axis reduces the sprinter's forward momentum, and the large area above the axis increases his momentum. The net effect is that his forward momentum increases, so his forward speed increases. In part B, once over the finishing line, the sprinter only tries to slow down, so each stride shows only a loop below the time axis on the graph. In part A, the forces on the sphere carrying charge Q1 are the downward pull of the Earth, W, the pull of the thread T at an angle θ, the horizontal push F of the charge on the other sphere. The sphere is in equilibrium. Resolving the forces horizontally shows that force F is equal to T multiplied by sine θ. Resolving the forces vertically shows that force W is equal to T multiplied by cos θ. Dividing these two forces gives this expression, and the right-hand side of this simplifies to tan theta. Rearranging this shows that F equals W multiplied by tan theta. Note that there may be no marks for the last step here because you are told what the final result is. In part B, you know that sine theta equals 37 millimeters divided by 440 millimeters, which leads to theta equals 4.82 degrees. We can work out the size of the force F as shown here. It works out to be 9.3 times 10 to the minus 5 newtons, which is about 0.1 millinewtons. Make sure that you show one more significant figure than asked for in a show that question. Part C is a straightforward rearranged Coulomb's law calculation. You'll need to look up the electric field constant K in the datasheet. Substituting and calculating shows the value of charge Q2 to be 2.8 times 10 to the minus 9 coulombs. Notice the describe and explain instruction. That means two different answers are needed. A list of bullet points will be the best way of presenting your answer. Describing what happens takes only one sentence. The explanation is much more complex and tests your understanding of an application of the law of electromagnetic induction. When the magnetic flux linking a circuit changes, the size of the induced EMF is equal to the rate of change of flux linkage. As the bicycle wheel rotates, the metal wheel resting against the rubber tyre rotates, and the lamp lights up. This causes the cylindrical magnet to rotate rapidly, producing a changing magnetic flux through the coil. The rate of change of flux linking this coil is therefore high, and an induced EMF is produced across its ends. Wires connect the ends of the coil to the bulb in the lamp housing, producing an induced current in the lamp. The light energy in the bicycle lamp comes from the kinetic energy of the wheel. The graph does not quite level off in part A, so an estimate is needed. It is about 5.4 times 10 to the minus 3 coulombs. In part B, the current at any time is found from the gradient of the graph at that time, so we draw a tangent at the required time and find its slope. The fact that the unit for the gradient is coulombs over seconds is a great help here. In part C, there are several ways of finding RC. You could try to read the time it takes for the charge to reach half its maximum value. In other words, the time t when the charge Q equals 2.7 times 10 to the minus 3 coulombs. The graph shows this to be 3.0 seconds. You would then use t half equals RC natural log 2, which shows RC to be 4.3 seconds. Here's another method, and it's possibly quicker. The tangent to the graph from the origin reaches the maximum charge stored at a time equal to RC. This also shows that RC is about 4.3 seconds. However, this method is unlikely to be better than about plus or minus 10%, unless a lot of care is taken in drawing the tangent. In part D, the fact that two methods are asked for but not specified makes this a difficult part of the test, especially in finding a second method. The first method makes use of the fact that RC is equal to 4.3 seconds, and that we know the value of R to be 8,500 ohms. Substituting and calculating shows that the capacitance is 5.1 times 10 to the minus 4 farads. The second method uses the fact that at the maximum charge stored, the charge stored equals the capacitance C multiplied by the potential difference V. Now we know that the potential difference in the charging circuit is 12 volts, so we can calculate the capacitance C. And it turns out to be 4.5 times 10 to the minus 4 farads by this method. In Part A, the centripetal acceleration can be calculated using the square of the tangential speed divided by the radius. First, we calculate the tangential speed v for the Moon's rotation using the time it takes for a complete orbit of the Earth in seconds. And it works out to be 1,020 metres per second. So we can now calculate the Moon's centripetal acceleration in this orbit. And it turns out to be 2.72 times 10 to the minus 3 metres per second squared. In Part B, at the Earth's surface, the free fall acceleration, g0, is 9.81 metres per second squared. Dividing the two accelerations gives the required comparison. The ratio 383 over 6.38 given in the question is about 60. The square root of 3,606 is about 60. So the ratio of the gravitational fields, 3,606, looks to be close to the inverse square of the ratio of the distances from the centre of the Earth. This is an unstructured calculation designed to test your ability in stretch and challenge questions. You will need to use the datasheet to find values for some of the constants in this question. Notice that you are asked to explain how, as well as to deduce a value. The orbiting electron is accelerating centripetally at a high speed. The centripetal accelerating force is the electric Coulomb attraction between the positively charged proton and the negatively charged electron. This can be formulated mathematically in an expression involving the mass me of the electron, its orbital speed v and orbital radius r, along with the Coulomb law attraction. This rearranges to give this expression for the square of the speed of the orbiting electron. Its orbital speed can be calculated, and hence its orbital frequency. Substituting the values from the datasheet, we get, and v squared works out to be 4.77 times 10 to the 12 metres squared per second squared, giving a value of 2.2 times 10 to the 6 metres per second for the speed of the electron. We can now calculate the frequency of the orbiting electron as shown here, and it works out to be 6.6 times 10 to the 15 Hertz. It's dangerous to go straight to your calculator answer for v squared without showing the values you have substituted. If you get it wrong, you will also lose the last mark, the correct value of the frequency f. If you get it right, however, you will get the credit. In Part A, the electric field lines do not go straight across from one tube to another, but loop inwards a little. The electric field between the tubes accelerates the electrons as they move between them, adding energy each time. The electric field also focuses the electron beam. In other words, it helps to keep a narrow beam as the electrons pass along the linac. In the first part of B, the electrons are shielded from the electric field when they are inside the tubes and therefore drift at a constant velocity there. Part B2 is a suggest question. Either of these statements will probably be enough. In part C, it seems rather obvious, but it is worth stating that the electrons acquire kinetic energy of 8.4 giga-electron volts. However, you will probably get the mark for using 8.4 giga-electron volts in your calculation. The increase in mass of each electron can be calculated using the rearranged energy-speed relationship. Substituting, remembering to convert electron volts to joules, and calculating shows that the increase in mass is 1.5 times 10 to the minus 26 kilograms. This is nearly 10 times the rest mass of a proton. A quantitative comment, that's one with numbers in, is usually best. In part A, both fields are uniform. The electric field is uniform because it is between two parallel charged plates. The gravitational field is uniform because it is near the Earth's surface. The big difference is that one is horizontal and the other is vertical. Part B is testing that the gravitational force on the dust particle, W equals mg, is acting vertically downwards, and the electric force on the particle, F equals EQ, is acting horizontally from left to right. Notice that part C is a describe and explain question. Deal with each aspect separately, but look carefully at the forces in the free body force diagram and note that they are constant forces. The two forces on the dust particle will add as two vectors to give a single constant force F. The direction of this force will be down and to the right at an angle theta below the horizontal. Under the action of this constant force, the particle will accelerate along this path. Particles with 3 quarks are called baryons, and those with 2 quarks are called mesons. The up quark carries charge plus 2/3 e, and the down quark carries charge minus 1/3 e. In the first part of part A, U bar D is a meson with a charge of minus 2/3 e plus minus 1/3 e, which adds to an overall charge of minus e, that is, minus 1.6 times 10 to the minus 19 coulombs. The other particle emerging from A carries no charge because it does not produce a trail of ions, so UDS must have charge 0. It is a baryon with a charge of plus 2/3 e plus minus 1/3 e plus minus 1/3 e, which tells us that the charge on an S quark is minus 1/3 e. We can now deduce that the DSS particle is a baryon with a charge of minus 1/3 e plus minus 1/3 e plus minus 1/3 e, which adds to an overall charge of minus e. In the second part of A, U bar D is a charged particle that will bend when moving in a magnetic field, unless it is moving very close to the speed of light. Because the meson is negatively charged, using the left-hand rule shows that the magnetic field is directed into the page. In the first part of part B, the proton is P. You are not asked to explain this, but P is the proton because charge is conserved at B, and we already know that the curved path from A is a negatively charged meson, so the charge on particle Q must also be negative. In part 3, you need to recognise that the tracks are curved. The magnetic force BeV gives rise to a centripetal acceleration. Using Newton's second law and rearranging gives the relationship shown. Now momentum is given by mv, remember, so the particle with the larger momentum is the one moving in the circle with the larger radius.